Hi guys, welcome back. So in the last video, I mentioned at the very end that a few people had asked about complex numbers in polar form. So what I'm going to go ahead and do is I'm going to do a couple of simple examples, and then I did have a specific question about question 19b. So I might do two parts to this video. I'll start off with the real basic stuff, and then we'll move on and look at the more difficult questions in a sec. All right, so starting off, determine the modulus of each of the following. So we've got to actually work out what I'm talking about when I'm saying the modulus and the argument. So when something's in polar form, I'm just going to quickly draw a little diagram here. So if something's in polar form, if I've got a vector or if I've got a point or whatever it is, I can look at two things. The first thing that I can look at is the angle of this line, so coming up from the x-axis here. And the other thing that I can do is I can look at the length of the line along here. So this angle here is called the argument. So sometimes it's called the argument of z, where z is a complex number. So if I write that, z equals a plus bi. So the argument of z would be the angle that is made by this particular complex number on an Argand plane. And then this here, this length of this line is called the modulus. So you might hear this referred to as mod z or something equally as bizarre. I think your textbook calls it mod z. And if I was talking about the modulus of z, I'm talking about the length of this particular vector on the Argand plane. So this first part here, it's asking us to find the modulus of each of the following. So to find the modulus, or to find the length of this line here, we're going to use Pythagoras' theorem. So we've used this formula a couple of times before. Let's pick a different color. Let's do I want black or do I want green? Let's do green. Let's do something different. So we've used this formula before. So the length of r is going to be equal to the square root of x squared plus y squared. So that's just come from the idea of Pythagoras' theorem. So if I call this my x squared, I call this my y squared, then this here is going to be equal to r squared. So the value r is going to be the square root of x squared and y squared. So now what I'm going to do is I'm going to substitute in the values that I know. So when I have something in complex number form, this real value becomes our x-coordinate and this imaginary value becomes our y-coordinate. Sorry, that was very tiny there, wasn't it? So let's substitute these values in now. So for this first expression, we've got 3 and 1 because the coefficient of this value for I is 1. So the square root of 3 squared plus 1 squared is going to be the values we're going to substitute in. Now 3 squared is equal, 3 squared is equal to 9, 1 squared is equal to 1, so if I add them together, I'm going to get the square root of 10. Now you can find this as a decimal value if you wish, so I'm just going to quickly put that in my calculator. So the square root of 10 is going to be 3.16. But I think because we're in specialist maths, I think I'm happy for you to leave it as the square root of 10 because that is the exact form. I mean, if we had another surd and you could simplify that surd, absolutely put it in the simplest surd form. And I think that's just a little bit more accurate than saying 3.16. So it's up to you. I prefer this one though. So if you could do it that way, that would be great. All right, so let's have another go. Let's have a look at this question here. So the modulus, so this value r for this question b here, is going to be equal to the square root of x squared plus y squared. So let's substitute in our values. So the coefficients out the front here are going to be 12 and 5. So that's my real component and my imaginary component. So this solution is going to be 12 squared plus 5 squared. 12 squared is 144. 144 plus 25 is going to be 169. And so the square root of 169 is 13. So for that one, it is a nice whole round number value. Okay, so I'm guessing you guys can go and have an attempt at C on your own. It's not too tricky. Whoops, what am I doing? Not too tricky. What I want to go through now is I want to go through the argument. So sometimes, remember, this is going to be referred to as arg z. The argument is just the same thing as finding that angle when we're given something in polar form. So let's go ahead and find that angle now. So to do that, to find this angle here, if we're given the value of r and we want to find the angle, What we can actually do is we can use our tan, or we could use our sine, or we could use our cos formulas, depending on the other information that we have. Now, luckily for us, they've actually given us the x and the y coordinate here. So this length here is going to be 8, and this length here is going to be 8 as well. So for this particular case, we don't have the r value. So we're going to use tan because we've got the opposite side and we've got the adjacent side. So that's a nice little tip here. So if you have tan of the angle is going to be equal to y over x. And so the angle is going to be equal to inverse tan of y over. All right, so let's substitute our values in now. So inverse tan of 8 over 8, so that's the same as saying inverse tan of 1 is going to be equal to pi on 4 radians. Okay, and that's all we need to do. So let's do another example now. Let's have a look at question B. So again, we're given the x and the y coordinate, so that's going to be 1/2 and root 3 over 2. So we're going to substitute that into our formula. Whoops. Y over x, and that will be equal to our angle. So our angle is going to be equal to root 3 over 2 divided by 1/2. So I'll just quickly pop that in my calculator and come back. And the answer that I've gotten for that one is pi on 3 radians. Okay, so that's just a couple of simple examples. Let's move on to a couple more trickier ones now. Okay, so here's another example of a good, simple, familiar question. So a little bit more in depth than the last one, but not too tricky. So express 15 cis 2 pi on 3 in Cartesian form. So when we have something that's written in this form, cis really represents cos plus I sine. So the way that we would represent this would actually be 15 cos, what was that angle? 2 pi on 3 plus 15 sine 2 pi on 3 I, because that's our imaginary part. So I'm going to substitute each of those into my calculator, and I'm going to come back. Actually, you know what I can do? I can show you how to do it on the graphics calculator. All right, let's bring up our calculator. So if we go into, so first things first, we have to make sure that this is in the correct mode. So I've already got mine in the correct mode, so I'll just show you how to change that. So if you go into Shift, Setup, and then you're going to scroll down until you see complex mode. Now there's 3 different forms here. So there's the real mode. So if you type in the square root of -25, for example, when it's in real mode, it's going to come up as a syntax error. So what you can do is you can change it into complex mode. So we can have it as just the Cartesian form, or we can have it as the polar form. So what we're trying to do is we're trying to convert from the polar form to the Cartesian form. So I want it in this A plus BI section. And then I'm going to hit execute. And then if you just double check up that top little button there, that should say A plus BI. All right, so let's type in our information now. So what was the question? 15 cis 2 pi on 3. So let's type that in. 15, and now we're going to use this funny little button, Shift, cis, and then 2 pi on 3. And we're going to hit execute. And so this is now in our Cartesian form. So let's jump back in and let's write that in our OneNote. So what do we have? -15 over 2. So -15 over 2. And then plus 15 root 3 over 2i. Plus 15 root 3 over 2i. So that's how we can calculate that using our actual calculator. Now, if we didn't have our calculator to do that, so let's say that this was a tech-free example. So what we would actually do is we would work out 15 cos 2 pi on 3, and we would have to go in and use our CAST circle and use those trig identities, so those special triangles. So the first special triangle is the 45, 45, 90 triangle, and that's the isosceles triangle. And then the other special triangle that we have is the 30, 60, 90 triangle, and that's the one that's like the root 3. I'm trying to remember which side goes where. I think that's right. Oh, maybe it's not. Either way, special triangles. And then we would have to go ahead and do it that way using our true identities. I think it's a lot easier just to chuck it in your calculator if you have the option to do that. Now, again, if you don't have a graphics calculator and you can't just chuck that in, you can pop it in your scientific calculator just using this, and you pop it in your scientific calculator, you're going to get negative 15/2 as your value for this, and then you would do the same thing. You'd put 15 sine 2 pi on 3 into your scientific calculator, and then that would come up with 15 root 3 over 2 for that solution there. All right, so let's do a different example now. So I really want to show you this using the graphics calculator again. So we're going to express negative 1 over root 3 minus 1 over 3i in polar form. Now, I don't really like the fact that they've done that as something that has an irrational number in the denominator. So you can fix that if you like. I think that they've done that though because I think this is supposed to be like a tech-free example and it wants you to specifically use those special triangles. But I'm not going to do that. Let's just jump in with the calculator. So the first thing I'm going to do is I'm going to change that mode over. So if we go Shift, Setup, and this time I want to change it so it's in the polar form. So I'm going to click F3 and then execute. And then now let's type in that particular value that we had. So one sec, what was it? So type in our calculator, negative 1 over root 3 plus, oops, that's not where I want it, plus, oops, that's the wrong thing. Oh, minus, doing well, aren't I? Plus negative 1/3 I. So let's find this I. One sec. Okay, so I'll just quickly show you where that little button I is. So I'll just go right back. Whoops, excuse me. Just go right back to the beginning of that. So if you go into Shift, oh wait, not Shift, sorry, just Option, and you go into Complex, and then that's that little I there. So that's all I did to put that little I in, and then I hit Enter. And so now this is telling me my solution here. So 2/3 cis, negative 5 over 6 pi. So let's go ahead and write that as our solution. So oh geez, I can't remember. Getting too old. 2/3 cis, and then what was our angle? Oops, that's the wrong thing. Negative 5 over 6 pi. So negative 5 over 6 pi. So that's in polar form. And again, we could do this just by using those equations that we did before. So this was my x coordinate, this was my y coordinate, and I could use that r is equal to the square root of x squared plus y squared, and then I could find my angle using tan negative 1 y over x. And again, I think they've given you this irrational form because they want you to do this as a tech-free question, but I think that's getting kind of crazy. I'd just rather do this as a tech-active example. So hopefully you guys have a bit of a better idea now about some of those simple examples. So I'm going to jump in, I'm going to do another video now with some of the really sort of tricky stuff.